Good morning, everybody. Thank you for joining us today. So this is a webinar on Introduction to FlowVision CFD software. My name is Kaniz and I'm the Marketing Specialist at Abaqus. And today we have Sinan as our presenter, who is our FlowVision expert. Just before I start the webinar, this is going to be about a 45 minutes webinar. At the end of the webinar, we'll have a short Q&A session. So if you have any questions, you can see the little Q&A tab at the bottom of the screen. There's also a chat tab. So if you can't hear us or if there are any questions, you can always type those questions in the chat section, and we will do our best to answer all questions at the end. So let's get started. Sinan, do you want to go ahead and give a little introduction of yourself?
Yeah, sure. Thank you, Kanes. So, hello everyone, and thanks for joining us today. So, I'm Sinan Soğancı, and I'm working as the Business Development Manager of FlowVision CFD software for the Capvidia company from Belgium. So, today it's very nice to be with you here, and I will try to explain you the unique modeling technologies and the simulation capabilities of the FlowVision CFD software. So I think now we will start with an introduction from Kanes, and then I will have the honor to take the floor back.
Okay, I want to get started with the introduction to Abaqus. Sinan, can we go to the intro to Abaqus slide? Okay, here's an overview about our company. We have experience in multiple industries, including energy and process, life sciences, manufacturing, high-tech, aerospace. We are headquartered in Houston, but we also have a presence in Chicago, Cincinnati, San Francisco, and Detroit. We have a highly experienced team consisting of PhDs and masters in solid mechanics, fluid mechanics, materials and corrosion, numerical analysis, statistics, optimization, and reliability. We provide virtual design experience through collaboration and data analytics. We also provide automation and customization. We also provide 3D printing and additive manufacturing simulation services. I also want to talk about our technical capabilities. We have experience in design analysis and virtual testing using simulation, fatigue, fracture damage, optimization and reliability, multi-physics simulations, composites, additive manufacturing simulation, simulation automation, and patient-specific simulation for life sciences. That is our overview. At the end of the webinar, we also have some information on how you can contact us if you have any questions about FlowVision. And Sinan, do you want to take over now?
So, thanks for this nice introduction. And now I'll be pleased to take the floor. And start my part by first talking about the Capvidia, and then the product FlowVision itself and its peculiarities in this scope. So first, a few words about the Capvidia as a company. Capvidia is a global software vendor, engineering software vendor in the areas of model-based definition and enterprise, reverse engineering, and computational fluid dynamics, which is our topic today. So our intention is to develop these software and use these software in the best practices with our users to simplify their engineering processes, increase the quality of their products, and reduce the costs of their overall engineering workflows. And about the organization of Capvidia, it's headquartered in Leuven, Belgium, and we have offices in several locations all around the world, including United States, Russian Federation, Germany, and Spain. And in addition to that, we have an international operation through channel partners such as the Wyas Corporation. And for more than 20 years now, we've been operating in this area with our own team of around 100 people, mostly engineers and scientists. And in overall, this international organization is completely a privately owned organization. And then starting with our main topic today, which is the FlowVision CFD software. First thing I would like to do is give you a brief introduction about what FlowVision is. FlowVision has been on the market for over 20 years now with its robust and proven technology. And one of the milestones is once the co-simulation with Abaqus started, and it was already in the 2002, intended for the strongly coupled FSI problems, and since then we have been still doing that. And as you can see on the timeline chart, we have been developing and distributing this software for a very long time, and in time we are changing the versions of the software, and still today we are using the FlowVision 3 version. And of course, this is a continuous development cycle. And the focus of FlowVision CFD software and its utilization is based on the advanced physics problems. And up to now, we were able to pioneer the solution of some CFD challenges, including the Tyra coupling, the simulation of screw compressors, leakages in ceilings, in the ceilings industry, and finally the human modeling. To do all these challenging simulations and in most of the time advanced and multi-physics problems, there are several unique capabilities that brings FlowVision beyond the competition, which can be listed mainly as the automatic meshing and the CAD associativity, the moving bodies and their modeling, the approach for the multi-physics simulations, and the unique clearance or gap model addressing the dimensionality problems. So this is not the whole story, and considering about all of these, I'll be talking and trying to explain you the approaches in the upcoming slides. Having said that, I would like to dive into the main differentiator technologies of FlowVision, and maybe on top of that we should be talking about the SGGR technology, where the abbreviations stand for subgrid geometry resolution. Here the idea is focusing on the real physics, a part of which is the real geometry. So here, as you can see on the left side of the slide, there are well-known meshing methodologies like the cut cell or the immersed boundary methods. But as you can see on the left bottom, FlowVision SGGR is the only method which keeps the CAD geometries as they are, without any simplification, defeaturing, or approximation. Absolutely. So, as you can see on the right-hand side of the slide, the finite volume cells that are being used in FlowVision are constituted of the CAD boundaries. Those green triangles are the CAD representation, and they just turn out to be the boundaries of the finite volume cell, which is completely unique and which is still the only methodology which allows you to work with the original CAD boundary representation without any modification on that. So if we look at the workflow, how we do this, this what you see is our initial Cartesian grid that we use in FlowVision. And the next step is usually importing here a CAD geometry, or in the FSI, fluid structure interaction simulations, the finite element mesh. And the next step following that is the mesh generation, which is completely automatic, and it covers the Boolean subtraction of this CAD finite element volume from the CFD mesh. And the result is that your CAD or finite element border becomes the CFD boundary, the finite volume cells. So each CFD finite volume cell contains one CAD or finite element border. Of course, if it's in the vicinity of a wall. So which allows not only accurate geometrical representation, it also makes it very easy to calculate loads accurately and transfer loads accurately for structural simulations and track the surface motions with the ultimate accuracy. Following that, if we have some closer look on the computational grid and how it's adapted. So as you can obviously see, we have basically a Cartesian grid, and then we have the adaptations. So the adaptations can be based on the solution, the gradients of flow parameters. For example, as you can see on the left, the computation grid cells are automatically adapted based on the velocity gradients. Also, the user can define adaptations based on values, some point values or interval of physical values, again, such as velocity, pressure, or anything, or for example, Y plus intervalence modeling that can be automatically used for adaptation. And in addition to that, geometry-based adaptations also play a vital role in reaching the ultimate efficient computation grids. So here in the middle, you can see adaptation on an arbitrary shape, which can be also moving in a transient simulation, which means that you will be adapting different regions with respect to time. And on the right-hand side, you see adaptations based on the geometry boundaries. Of course, the adaptation levels are also defined by the user. Followed by that, another peculiarity of FlowVision is how it approaches the moving bodies. So we define the movements in 6 degrees of freedom, which one or group of them the user wants to use, and there can be made independent movement definitions for each object and axis. And I will be defining in a minute how to define those movements. And a very important remark here is that the movements in FlowVision is not limited by intersections of bodies or even the full closure situations, like when two bodies come into full contact, separate the flow field into 2 or more pieces. This is a straightforward application in FlowVision, where as you can see on the left, a moving body can get out of the computational domain, can get back in the computational domain, or as you can see on the right, on a gearbox from the automotive industry, we have the gears rotating, we have the bearings rotating, we have very small gaps between them, and also some parts are touching each other. And also you can see this is a multi-phase flow, so all those can be included in a simulation without any limitations. So to be able to do all these, the mesh is very critical, and always we don't do any mesh deformation. And here maybe I need to make a reminder that we were talking about the subgrid geometry resolution technology, and as bodies move, that technology is always active in the background. So as the bodies move, you always resolve the boundaries as they are without any loss of accuracy. So once the bodies change location, mesh is renewed automatically, and FlowVision is not expecting any user manipulation to do that. So the motions can be defined like translational and rotational velocities in any axes defined by the user, dictated by the user, or user can define external forces and torques, and using the inertial properties, FlowVision can calculate the motion, or there can be the rigid FSI where the bodies are allowed to move under aero or hydrodynamics forces. And finally, there can be some external coupling where the movements are coming from finite element software, some optimization software, in some cases from motion capturing recorded movements, or in the living heart human model from the Dassault system simulator where the heart movements are being transferred from Abaqus software, which are previously defined there. So all kinds of movements and all kinds of definitions can be used in FlowVision. And again, considering the moving body, finally some examples. In the right-hand side, we're focusing on the geometry replacements during simulation. As we can see, the rotor on the right is changing during the course of simulation. And here, you can even change the computational domain itself by just simply through the interface, writing simple scripts through a couple of very user-friendly methodologies. And on the left-hand side is a typical example of the full closure from an internal combustion engine. When the valves are at the top dead end, the inlets and the main chamber of the engine are separated from each other, and the flow field is completely divided. And this is, as I said before, in a straightforward manner, can be tackled with FlowVision. The next topic I would like to focus on is the fluid structure interaction. And here, more specifically, our focus is on the two-way strongly coupled simulations. And the message we are trying to bring, and that we have been doing for some long time, is the reaching accurate FSI simulations, reasonable results, with a flexible workflow. This is not a burden as assumed by a huge simulation community. So first of all, considering the accuracy, again, here we are inserting SGGR into the game here, which allows the finite element boundaries to be accurately, without approximation, represented. And also this gives us the chance to make completely matched, automatically mapped, accurate data exchange between the CFD and finite element domains. And here the examples you're seeing are on the right-hand side, the Living Heart project, led by the Dassault system, where we have the heart expansions, contractions, and also in this sample, the mechanical heart valves. And on the left-hand side, what you see is an artificial aortic heart valve, where this is also, maybe I can, this is also a two-way strongly coupled fluid structure interaction case where the leaflets of the valve are touching each other, and at some instance the flow is completely not allowed to pass through the center of the valve. So the next question is how we do this. First of all, one of the messages is that there is no need for third-party software to match CFD and finite element codes. So what we have instead is what we call the multi-physics manager, which is controlling both FlowVision and similarly Abaqus software during the co-simulation process, and which is allowing a very simple, smooth setup, start or restart of simulation, which sometimes are assumed to be the burdens for the FSI, and which allows also the real-time results monitoring. Here, during the coupling, the coupling to be automatic and also the remeshing to be automatic are critical aspects that for the user, what should remain from our perspective is that the user should be focused on defining the correct finite element model, defining the correct CFD model, and an accurate data exchange is duty of multiphysics manager. And we have been doing this, as I said, already for a long time. And then you see in the middle some calculation steps as a sample. And here the thing is, in such a process, to be able to make sure about the accuracy, the time steps are important. And here in this respect, we define 3 independent time steps, which is the finite element, CFD, and data exchange time steps. These 3 all should be independently determined, just focused on the time scales of each physical aspects. This ensures not only accuracy, but also the computational performance and efficiency, which is rather very critical in FSI tasks. The next topic I would like to talk about is FlowVision gap model, which is intended for dimensionality issues, where the dimension ratio is even going up to 5 to 10 over 7. And also the clearance flows, where the channels are down to sizes of sub-microns. So you have a very small clearance, and then you have a large section of flow. So you result with a dimensionality issue, which makes it almost impossible or very computational demanding to resolve with traditional meshing approaches. So starting in the beginning of 2000, this methodology was developed for the script compressor industry first. And the idea just very basically was to manipulate the momentum equation based initially on a Pusev flow assumption, and further developed for in the beginning for a couple of years by analytical and empirical research and development, of course, thanks to our partners also from the script compressor industry. So this was the beginning. And then still for years, we have been using and validating our gap model by experimental data from various industries and applications. And looking at all those is what we say is that this is the most famous applications of the gap model are, of course, first still script compressors, following is the electronic assembly cooling, where you have a large number of components, up to a couple of hundreds, where you have very small distances between these components. You have the momentum and heat transfer at the same time, so we can address them with FlowVision in a very efficient manner. And also, as you can see on the right top, the launching cases, underwater launching, in air launching, some ammunition. Here you can see those purple gap cells, which allows for simulating the flow field in this region just with one row of cells. So this is the main idea here. This is a very typical example of a dimensionality problem. So here you have a very small clearance, and then you have a large region. You will most probably adapt the cells in the up and downstream of this ammunition piece, but still here you have a very small gap. And gap model allows to resolve the flow in this area with only one row of cells, as you can see in this picture. And now, following that, I would like to show you a more clear example of the gap model where it was born from the script compressors. Here on the right, you see the rotor and the housing. And here the clearances are usually in the orders of microns. And the diameters of the rotors are usually like 30 or 40 centimeters, like as a magnitude. And here in the animation, you see the purple boxes, which are the gap cells, which are automatically identified by FlowVision during the course of simulation. And the equations on those regions are also automatically manipulated. So how this works, you see some screenshots from the interface. As a user, all you need to do is activate the gap model and define the minimum and maximum clearances which you want FlowVision to address as gap. Then FlowVision detects those. This can be transiently changing and manipulates the local calculations there. So this is really changing the game if you have small clearances. And good news is this you can obviously use with moving bodies. This you can use with multi-phase simulations, and gap model you can still use with the fluid structure interaction cases, which is also very helpful in cases, for example, the sealing applications. And the next topic of mine is the multi-phase methodology, and specifically the advanced volume of fluid method. I'm sure the volume of fluid method is already well known from literature and from most of the CFD software available on the market. So what we are doing here is the representation, the tracking of the free surface. So here we again play the card of the subgrid geometry resolution, and then we move the WOF methodology one step forward. So instead of just representing each cell with a percentage of phase existences, we reconstruct the free surface with the SGGR technology. So the result includes the free surface topology. So that this allows simulations like you see on the right, which is a space re-entry vehicle landing on sea with some supersonic jets which are trying to decelerate the object. And then another important aspect is what we call the exact mass conservation, because in the typical WOF applications, once you have small droplets in your flow fields, after some level of sizes, they just start to disappear. They are behaved as numerical errors. But here, even if your droplets are in subgrid level in regards of size, their masses are still conserved. So what it means, so if we consider such an gearbox simulation, again from the automotive industry, where the oil is just spreading around with very small droplets, smaller than your grid, here we can still capture those droplets. And the thing is, these droplets, we keep their masses moving through grids which are larger than those droplets, and once they get back together and form a mass that is almost equal to your cell sizes, FlowVision again starts simulating it as a bulk flow. So you keep them, and those droplets can join back to bulk flow or vice versa, resulting in accurate multi-phase representations. Then a few words about the solver and also the flexibilities it brings. In a CFD project or a FSI project using FlowVision, you can have laminar and turbulence modeling in same project in different regions of the domain. That's obvious. And then I think a very nice helper, a convergence booster, is the capability to define and assign different time steps for different physical processes, such as heat transfer, momentum, turbulence. And this is a capability which allows to significantly speed up your convergence. Assume in a simulation you have different orders of magnitude of time scales for momentum and heat transfer, which is very likely to be observed. In such cases, you can still continue resolving the momentum with very small time steps, and you can just get back to heat transfer at some intervals, which means that you are using a larger time step just for heat transfer equations. And also just maybe in some region of the domain, you can change this. Then considering different flow regimes represented by different Mach numbers, starting from the incompressible, subsonic, transonic, supersonic, and hypersonic. So since we are working in the space industry, we also already have the experience with the hypersonic flows. So up to that, we have only one universal flow in FlowVision, and it has the duty to capture the shock onsets and then the shock wave interactions and movements throughout the flow field. So to do those, you are not, as a user, expected to address at which specific region there is transonic or, let's say, hypersonic flow. Then another flexibility or user friendliness aspect is the FlowVision formula editor. As you can see, it seems like a simple calculator, and this you can open it, definition of any kind of boundary condition or any kind of settings. Instead of entering just a constant value, you can easily open this window and start writing formulas. And any calculated parameter can be used here as an input. The main things like time, of course, you can already use, but apart from that, like the average pressure on some surface, average temperature on some volume, maximum value of total pressure at a specific location, whatever, if it's calculated in the CFD equations, here you can use that to make some other variable as a function of that calculated variable. And to do so, what you have as scientific or mathematical capabilities are you can use both scalar inputs and vectorial operations. You can use local and global variables like a velocity value in a boundary condition, like you enter one value there, but then you can use the local velocity at each coordinate to define something else. You can use the logarithmic functions, you can use the trigonometric functions, sinusoidal equations, for example. And for me, the most important side is that you can use the logical operators. I think the most famous being the if conditioning. Here I would like to give you an example of that. Definition of porous resistance in a porous medium modeling as a function of local velocity. So the equation entered here is first we define a variable rho which is dependent on time as a if condition. And again, a good news is that this is just the Microsoft Excel syntax, so we're not expecting any user to be competent on coding things, compiling things, etc. If you know how to write a mathematical expression in Excel, okay, so you are set to go. And then here in this example, once you have the rho as a function of time, then you define the porous resistance as a function of rho and also the local velocity. So at each different coordinate, at each different cell, we have different resistance since the local velocity is different at each different cell. And these are just called from the simulation data at each time step from FlowVision. Then also the user experience starting from the installation. One important sentence, like we are talking about complex cases, multi-physics cases, fluid structure interaction cases and everything. But on the other hand, if you have just a correct CAD, not degenerated, not having problems, if it's fine, this is maybe the only thing to be ready before the simulation. And then you can prepare the most complex cases almost in half an hour, including the meshing and everything. I mean, starting with just the CAD and clicking the run button, I mean, from the simulation engineer literature, I can say. The installation of the software in either Linux or Windows machines, laptops, workstations, cluster, whatever, just in minutes. I mean, when I say minutes, it's less than 10 minutes, more specifically. And then the user's adaptation to the interface only in days, in couple of days, you will be completely fine. And then we, considering the large clusters, we have a high level of scalability. So we have practical applications up to a couple of thousands of cores. Also considering the licenses, all FlowVision licenses are naturally floating, so we don't have a license, like a standalone license. And then we have the full client server architecture. So you can have the all FlowVision models in just one computer. You can have the modeling on a simple laptop, including the meshing and everything. You can model those in a simple laptop. You can get your license from a server, which is physically located near you, or which is also physically located somewhere else. And then you can post your solutions to some computer. I mean, if you just have the network connection, you can do it. And we have the complete full flexibility in installation and utilizations. In overall here, I think we are proud to say the word that FlowVision is IT friendly. I mean, not only user, but also IT friendly is a nice word to represent this. And as a conclusion, I would like to quickly list what I've been talking about, what makes FlowVision CFD software unique, and what you can address with these unique capabilities. First thing was the subgrid geometry resolution, and this is addressing high fidelity representation of CAD and finite element models. Here, high fidelity is I say it like using the CAD and finite element boundaries as they are. This is the highest fidelity actually you can achieve. The capability of moving bodies, if you have some complex movements, intersections, full closure situations, so you're welcome to use the moving bodies technology. And a gap model to tackle the dimensionality problems, like micron or sub-micron clearances, and on the other end, centimeters or even meters of large volumes, large fluid volumes. So here we have the gap model to address those. And the two-way strongly coupled FSI approach with, especially with Simuli Abaqus software. So here, why it is different from the maybe other solutions. So we are easily addressing the very large deformations, also complex movements, coupled with that, contact situations, again, full closure situations, change in fluid volume and big change in fluid volume. So these can be addressed with our approach and experience. And the advanced volume of fluid approach. So if you have some small droplets, of course, small is a relative word. So here we are talking about smaller than your grids. And if you want to still track them, here the advanced WOF is helping you. And the thing is, this technology can be used together with fluid structure interaction or moving objects. So here again, I think this is a good type of simulation to address. And finally, the flexible settings and the smooth user experience. So here, if you have some very long or sometimes even impossible problem setup, or the simulation runs, if they are not feasible and if they cannot be fitted into your company workflows, engineering design workflows, again, these flexibilities are likely to help you, we hope. So actually, I'm just at the end of my presentation. I would like to thank you all for listening on behalf of YAS organizing this event. And if you're interested in FlowVision and what we're trying to tell you right now, please feel free to ask for some detailed information, or if you're interested in trying the software, if you want to start a pilot project, if you want to get to know more about the modules, the license configurations, and get some codes about it, or if you want our teams to do a project or consultancy work for you, so we will be here ready to listen to your queries and remarks about the presentation and FlowVision itself. So here, that's all from my side, and I would like to thank the whole audience listening to me, and I would like to thank again the Wayas and Kanes here for organizing this. So I think we can continue with the Q&A session.
Yes, thank you, Sinan, for the excellent presentation. If you guys have any questions, please feel free to contact us at support@viascorp.com. We do have expertise in training, software, and consultancy services. Now we are opening up the Q&A session, so please feel free to send us your questions. And it looks like we do have one question here.
Yes, I think I'd be pleased to answer that. Questions coming from Monica about the difference turbulence modeling options. And actually, Monica, you didn't miss it. I mean, I just tried to be as clear and short as possible, so I didn't focus on that part. Yes, basically, we are using the Reynolds averaged Navier-Stokes models in our cases. We have a number of turbulence models, like I think at this moment 4 different K epsilon models, one of which is being completely unique to us, and we call it the FlowVision K epsilon. And then we have the well-known Polar-Talmaras, Magorinsky, shear stress transport, and maybe I'm missing 1 or 2 more turbulence models in coupled to that. And again, maybe some information about the turbulence modeling, that we, of course, have the Wolf function approach and enhanced Wolf treatment approach. And considering the Wolf functions, again, we have some from literature, and we have our own also. And based on our experience with the users from the aviation industry, the aerodynamic designers, they more frequently use the FlowVision Wolf functions and also the enhanced Wolf treatment no Wolf function approach. And here, a good aspect, a positive aspect, is that we have very accurate results, like compared to aerodynamic experiments in a region like y plus equals to 0, between 0 to 2, with without Wolf functions, and starting from 5 to around 300 with Wolf functions, meaning the dead zone being trapped in just only between y plus equals to 2 and 5, I think, which is also helpful for turbulence modeling. There's some other question. Again, I'll be very pleased to address that, coming from Ian, about the solids parts being part of the domain or not. Yes, I mean, if you're using only FlowVision at this moment, I'm assuming that you don't have a finite element solver coupled with that. If it's only FlowVision, you can have solid parts like steels, for example. And basically, you can use them for conjugate heat transfer and heat conduction in solids. So this is something that we are doing. I guess this is what you're asking for. So then we have the rigid FSI, where the material properties is not to be very important. but the inertia, mass and moment inertias are important, and they are being used for motion calculation. Then we have the coupled fluid structure interaction cases in the end. So here, of course, you have the material definitions in the finite element part. So I assume that we can address most of the potential solid usages in a CFD simulation. But if that's not the whole what you're asking for, so please feel free to raise more details about the question, and I'll be glad to answer that. So yeah, there is, I think it's already being answered by Kanes, that through the chat screen we have, I think, a question about whether it's possible to get free trial licenses. So yeah, I would be pleased new people, engineers, to meet FlowVision and get to know what it can or cannot do for their cases. So we'd be glad if you get contacted with us, and we can have some discussion on your specific case, and we'd be pleased to start a trial with you. And considering the slides, not exactly this, but some portions of these slides are being shared. But again, if you're specifically interested in something, please feel free to again contact us and ask for that. I think overall, this presentation will not be available, but pieces I think will be available, because there are some also cooperation material here.
Yeah, I would like to add that this webinar is being recorded, so you will receive a recording of the webinar, so you will have access to the entire thing.
Yeah, that's even better. Yeah, very nice
Yeah.
point, guys. Thanks.
Yeah, I will send it out to all of our attendees.
Okay.
All right. I think we have some more questions.
Yes, let me try to go one by one. Yeah, consulting through WIAS using the FlowVision software. Yeah, this is completely possible. And here I think this is a perfect match to get most of the capabilities I've been trying to explain. Yeah, because WIAS has already a huge experience in the CFD area, and so you can get the consultancy or project work from them. This is completely available, and again, we'll be glad to get in contact for details about your needs and how we can address those. Yeah, again, Kanezi, I think you also make some additions. Yeah, please contact the support@wiascorp.com, and we'll be glad to maybe arrange some meetings to discuss your specific needs. Another question about the user conferences. Yeah, actually last week we had one, but it was in Moscow. In US this year, no, we will not have a specific FlowVision user conference, but we are planning to attend different events, and most probably the Simuli Abaqus events, for example, we are usually attending to show the FSI applications. But apart from that, this year, no. Next year there can be, because we have the WIAS as a value-added partner, and we have the offices and we have users there. This is a possibility. But apart from that, if you're specifically interested in one area, one industry, and where you would like to see how we apply FlowVision, because today in this limited amount of time, I was able to show just a couple of samples to give you the idea. That was all. But of course, if you're interested in specific area, obviously not violating the proprietary rights, we'll be glad to get back to you with more application samples.
All right, are there any more questions? I think we're good here, Sinan.
Oh, think so.
All right, thank you everybody so much for attending, and we will be sending out a recording of this webinar to everyone. And if you guys have any questions, please feel free to email us at support@viascorp.com. Again, thank you for attending and have a great day. Thank you, Sinan.
Thank you, Kanes. Thank you, everyone, for attending today. Hope to meet you again soon. Bye-bye.
All right. Okay, bye-bye.